Alright guys, I'm going to take you through the reaction rates lab in my kitchen with chemicals I stole from school. #rebel. So the first one that we're going to go through is the presence of a catalyst. So in this lab it says contain 2 test tubes. I have 2 beakers and fill each one with 3% hydrogen peroxide solution. So here I just went to Walgreens and got my hydrogen peroxide solution, and I'm going to put a little bit into each beaker. Okay, so hydrogen peroxide naturally over time does a decomposition reaction. So this looks like water, and the formula for hydrogen peroxide is H2O2. So actually what happens is that extra oxygen will slowly come out of this, and if you leave it sit out long enough, it will turn into water, okay? However, this happens very, very slowly. But in my second beaker, if we add a catalyst, which is a piece of a potato, so I have potato, cut a little part off of it, if we put that in and let it sit, do you guys see the bubbles coming off of it? So you can really see all of those bubbles coming off of it, whereas the other one does not have those bubbles coming off. So it's something that's happening anyway, but we added a catalyst. So a catalyst is speeding up that rate of reaction. And if we move my phone, you can really see inside, you can see all of those bubbles happening in there versus the other guy. So that is the first reaction. So write down your reflections on your lab and we'll move on to part 2. Alright, so with part 2, we are going to be experimenting with concentrations. So here I have a bottle of hydrochloric acid. So this is 1 molar. Molar just means a concentration. So I'm going to put some of my 1 molar hydrochloric acid in 1 beaker. And then in my second beaker, I am going to put 1 molar hydrochloric acid, but off camera I'm going to add in some distilled water to make the concentration a little bit more dilute. So for the next part of the reaction, I have my diluted hydrochloric acid and my concentrated hydrochloric acid. So the concentrated is in the little container, and I also have some pieces of the metal zinc. So these little pieces of metal will react with the hydrochloric acid to give off hydrogen gas and create zinc chloride. This reaction is also exothermic, so it generates heat. So when we put this into the dilute solution, we can see some bubbles coming off of it, but not a ton. And then when I add it into the concentrated solution, we can see a little bit more bubbles coming off of it. So this is the zinc that is in the dilute solution, and we can see there's like a little bit of bubbling around it, but not a ton. And if we look over at the other one, see how there's more bubbles on the outside of that zinc compared to the other one? So this reaction is happening slightly faster, and my solutions are more dilute, but it's the HCl I could get. So more diluted, less bubbles, more concentrated, we can see that there's more bubbles on there. So the reaction is happening faster. So for our next one, we're going to look at temperature. So here I have 2 beakers of just tap water, and one of them I'm going to go pop in the microwave for 45 seconds to a minute just to make sure that this water is hot, and then the other one is going to be room temperature. So I got my hot water, got my cold water, and what I'm going to do is I'm going to put in these denture cleaning tablets. I'm going to put 1 in each and see the different rates of dissolving versus hot water and cold water. Alright, so I'm going to drop these guys in very fast. Oh, look at our different rates of reaction. So remember, this one was hot water and this one was cold water. So write your observations down. Oh no, it's going to overflow. I'll be right back. For part 4, we're going to look at surface area. So I'm going to use the same denture tablets, but one of them I'm going to leave whole, and one of them I'm going to crush up, and crushing it gives more surface area, and see which one dissolves faster. Alright, so I got my one denture tablet all crushed up, and I have my other one that's whole. So the one that's crushed up has a ton of surface area. So if we think about the surface of every single one of those little tiny pieces, is much greater than the total surface area of this whole piece together. So we're going to drop both of these in at the same time. So already we can see which reaction is happening faster. So the one that has more surface area, that one is dissolving way, way faster than the one that has less surface area. All right, so as far as surface area goes, we have a second bonus experiment that is all about survival. So here on my neck, I actually have my fire starter. So I'm gonna take this off and show you guys something really, really cool. Hey, Duke. He says hi. Okay, so with my fire starter, basically what you're doing is you're taking this piece of ceramic or something really hard, usually like a rock or a flint or something like that, and what you're doing is you're gliding across a magnesium bar. So if you guys remember the first video lab, I showed lighting magnesium on fire. Magnesium is really, really flammable, so that's actually what creates a spark. So we can do that and create our little sparks. I don't know if you can kind of see me throwing them off there. And remember, don't try this at home. I'm only doing it right now because my husband's not home. Otherwise, he would totally yell at me. So when we're doing fire starting, you want to make sure that you're not like, I'm just grabbing things that are close to me. So like this piece of wood, if this was a branch in the woods, you don't want to just like try to start a branch on fire. It's not going to light. You need to start with stuff that's really, really small and fluffy, like dried grass or pine needles, or even take a piece of bark and like shred it up into like a little fluff ball. And the reason why is because it has more surface area. So if I want to get something to light, here I just have a Kleenex because it's raining outside right now and I can't really find any dry things. So what I've done is I've shredded this up so it has a massive, massive surface area. So now what I can do is start throwing sparks. And I lit my fire, so now I can survive the virus. Yay! All right, so for the further analysis part of this, in order to increase the rate of reaction, reactants must collide more frequently and have proper orientation in respect to one another. So with this, I want you guys to try to answer all of these. So why does increasing the concentration of the reactant speed it up? So remember, they have to collide more frequently. So here's your hint. If we have more concentration, do we have more or less molecules to collide? Okay, so keep that in mind. When things are hot, molecules actually move faster when they're hot. So for reactions, if they have to collide more frequently, if they're traveling faster, what's going to happen with their frequency of collisions? Crushing up a solid into a powder. So we did that one. If they have to collide more frequently, what is going to be more frequent collisions? Somebody throwing a basketball at you or cutting that basketball up into a bunch of little pieces and throwing all those little pieces at you? Which one's going to collide with you more? Stirring the reactants. How is that going to increase the collisions? And then decreasing the volume for gaseous reactants. So what we mean by that one is if I have a container with a gas in it, so we have all these gas molecules that are floating all over the place. If I make the container smaller, so I take that container and I squish it down so it's even smaller, are those molecules of gas getting closer together or are they getting farther apart as you squish them together? And as things get closer, are they going to collide more or less? So think about it that way.